In this video, we're going to explore injective and surjective linear transformations. So what an injective linear transformation is, we have this linear transformation from the vector space U into the vector space V. Then T is injective if whenever the outputs, or in other words, the images of X and the images and Y are equal, then X has to equal Y. So in other words, the pre-image X and the pre-image Y have to be the same if their outputs or their images are the same after I've done that transformation. We think of this as being onto, quote, onto. So when it means that we are injective, that means that my elements in U, UI, will only be mapped to one and only one element in V, V sub K. So as an example, we've got these two elements in U, which is U and W. If they're both being mapped to the same element V, then that is not injective. For it to be injective, there's one element in U that gets mapped to or transformed to only one element in V. And we can have some spare leftover elements in V, but everything in U has to be mapped to one element in V and only one element in V. So it doesn't matter that I've got extra elements in the codomain for injective. So for it to be injective, that part doesn't matter. Now, when we're talking about surjective, now suppose that T is this linear transformation and T is surjective for that every element in V, there exists a element in U, so that when I do the pre-image onto V, so the transformation of U onto V, is there has to be an element in V. And we want to think of this as being like 1 to 1. That means that every V has at least one, so it can have more than one. This one we can only have one. So every element V, which is our codomain, has to be matched up to at least one, could be more than one, element in our domain. There's a perfect one-to-one correspondence between the members of the sets. So here's an example visually of what a surjective and a non-surjective. Now notice that this is non-surjective because I have these elements hanging out right here in my codomain that are not being mapped to anything. So surjective means that I can have more than one element in my domain mapped to, or have a linear transformation that maps me to a codomain element. Now, we're also going to talk a little bit about the bijection or bijective linear transformation. And so when we have a bijective linear transformation, that means that there's a linear transformation, and T is bijective if there is, for every element in the codomain, there exists an element in the domain, so that the only time this happens, that when the outputs are the same, is when my inputs were the same. So the only time my codomain values are the same is when my domain values were the same. And so so we say it is both injective and surjective, one-to-one and onto. The one-to-one correspondence are invertible when it is a bijective linear transformation. So here's an example of a bijective linear transformation. I have U1 going to V1, and then it gets mapped back. U1 to V2, and it gets mapped back. The 0 element gets mapped back. And so if we're asked to determine whether or not our linear transformation is surjective, bijective, or injective, then what we have to do is we have to give you some more theorems, some more definitions, and then we're going to do some practice problems. So we're going to define what a kernel of a linear transformation is. What the kernel is the set of elements in U. So the set of elements in my domain that gets mapped to the 0 vector in my codomain. So in other words, we're saying all of the inputs that are being sent to the 0 vector. So that's what it means. Now we're going to talk about some important theorems that will help us as we practice whether or not our linear transformations are surjective, injective, or bijective. So the first one is that the kernel of T is the subspace of U. Now remember, the kernel of T is a set of elements in U that are mapped to or are sent to the zero vector in V. And the kernel itself will be a subspace of U. So everything that we know about subspaces will hold true. The next one we have is if it's a linear transformation and V is an element of my codomain, then the pre-image must be non-empty. And so in other words, I'm going to have that transformation and I'm not going to have anything that is left over. And the U must be the pre-image of V. And the pre-image of V must be set equal to the kernel. So U plus the kernel will be what the pre-image of V would be. Now, the one I did here in red is kind of important, and it's going to help us out, is that if this is a linear transformation and T is injective, it is injected if and only if the kernel of T is trivial. So if my kernel is non-trivial, then in other words, when I'm looking at my solutions, what we'll do in an example here in a minute, if it is non-trivial, then it is not injective. Okay, so that's kind of important. If U onto V is an injective, so we're assuming it's an injective linear transformation, and then the set S is a linear independent subset of U, then the image of S, so in other words, all of those elements mapped into our codomain, we'll call it R, is also linear independent. So if it starts linearly independent, then it will end up, when we've done our transformation, it will also end up being a linear independent set. That's if it's injective. Now, if U onto V is a linear transformation and the basis B is a subset or is a basis of U, then T is injective if and only if the image, that is, the codomain values, is a linear independent set. So if we know we have a basis and it gets sent to, and we know the basis, it is the basis of U, so that means of course that it is linearly independent and it spans the set. So if B is my spanning set that's linearly independent, spans all of U, then it's injective if and only if the image of B, so in other words my outputs, are linearly independent and a set of V. So we can check for linear independence too, if we start out with a basis. Now, if the transformation is an injective linear transformation, then the dimensions of my domain are less than or equal to the dimensions of my codomain. This tells us that if T is 1 to 1, then the dimensions of U must be less than, and that actually should say is onto, not 1 to 1. So it should be onto, because this is onto. So also look at dimensions. If the dimension of U is larger than the dimension of V, then we know that it is not going to be an injective linear transformation. So that's another check that we can do. And then of course we get the composition. If U and V, and if the linear transformation T from U to V and then linear transformation from V to W or an injective linear transformation, then that composition where I go from U to W is also an injective linear transformation. So let's practice this. So determine if the linear transformation is surjective, injective, or both, which means it is bijective. So here's my linear transformation, and it's given by this. I'm going to start out with a 2 by 2 matrix, and when I get done, this is what I'm going to do to it so that it is ADX squared minus BX plus C. Now I'm trying to determine whether or not it's in surjective, injective, or both, and both. So the first thing we're going to do is say, well, the typical element in P2, polynomials of degree 2 or less, has this E, and usually we do AX squared plus BX plus C, but we've already got A, B, C, and D already used up here, so we start out with the next letter, which is E. EX squared plus FX plus G. Thus, for this to be onto, we need to be able to find a solution to this, that I have a minus d x squared minus bx plus c has to equal e x squared plus fx plus g. Now, if we compare up the coefficients, a minus d has to equal f, so a minus d has to equal e, excuse me, and negative b has to equal f, and then of course we have c has to equal g, because that has to hold true. So then we know that this has an infinite number of solutions. As an example, one of the solutions is if d is equal to 0. If d is equal to 0, then a would equal e, and b would equal negative f, and c would equal to g. So we know, since this has an infinite number of solutions, t is onto. Especially, and as a special case, if e is equal to f is equal to g is equal to 0, then this gives us the solution of a, d is equal to 1, and b, c is equal to 0. So we'd have this transformation, that this 1, 0, 0, 1 would go to 0. So that the kernel itself is non-trivial. Thence, we know that t is injective. So we know it is both onto, and it is not going to be one-to-one, nor is it going to be bijective. So we have onto, it's onto, so it is injective, but it is not surjective because I don't have my kernel being empty. So that means it's not bijective. So let's talk about the definition of range, because we're going to use some more of the definitions to look at the important theorem outcomes to help us do the next example. So suppose that we have this linear transformation, then the range of t, is the set where it is going to be the outputs or the codomain when I have the element of u being in my set u, my vector set. So that's kind of important, because now that we have defined it, then if this is a linear transformation, then the range is a subspace of V, which is what we expected. And if U onto V is a linear transformation and T is surjective, if and only if the range of T equals the codomain. This means with the other theorems up above is that injective linear transformations have small or trivial kernels, and surjective linear transformation have large ranges. So then we get the next outcome, which is if T is a linear transformation and S U, it spans U, then the image of S, that is the R is equal to the T of the preimage and then all of that, it will span my range of T. So if I start out with a spanning set in U, then the transformation that's going to happen will span the range. It doesn't necessarily span V, but it will span the range. Now, if U down to V is a linear transformation and V belongs to the range, if and only if V will belong to the range of T, if and only if the pre-image of V is not the empty vector, so the non-empty vector, so it's the non-empty set, as I should say. So then, as an example, this is what I mean. So if we have the U plus my kernel of T can be mapped to V, and I have the pre-image of V2, which is going to be U2 plus the kernel of T can be mapped to V2. And of course, my 0 vector, which is equal to the kernel of T, is going to be mapped to the 0 vector here. And then I also have this one, which is the pre-image of V of 3, which is U3, pre-image, is going to go to V3. So then if T is a linear transformation and B is the basis of U, then T is surjective if and only if the image of B, that is this subset, it's the spanning set for V. So the basis in my original function, or my original domain, has to be their outputs. When I put it in and I get it mapped to this set, it has to be the spanning set for V. If T is a surjective linear transformation, then the dimensions of U is going to be greater than or equal to the dimensions of V. This tells us that T is not onto, but 1 to 1. 1 to 1 when the dimensions of U is greater than or equal to the dimensions of V. So then if T and S are linear transformations, we get the composition. And then, of course, here's the last big one, which is if T is a linear transformation where U and V are finite dimensional sets, vector spaces, then the dimension of V will equal the dimension of the kernel of T. The dimension of V is going to be the dimension of the kernel of T plus the dimension of the range of T. Kind of important too. Let's take a look at this example here, and we're trying to determine whether or not is injective, which is 1 to 1, surjective onto, or bijective, which is both 1 to 1 and onto. So here's how I'm going to define my linear transformation from R4 into R3. Here is R4. I have 4 entries, and I'm going to define it into this being R3. I really only have 3 entries. I have things going on in each entry, but only really have 3 entries. So I'm first going to start looking at the kernel, and what I need to do is make sure that it is a non-trivial element. There's at least one non-trivial element in the kernel for this to be injective. So that was one of my big theorem outcomes. So I'm going to go ahead and solve this homogeneous system. And the way I'm going to do that is I'm going to put that into a matrix, a coefficient matrix, because we know that we can augment on zeros and it's not going to do anything for us. So here is my coefficient matrix for this homogeneous system. I reduced row echelon this, and I get this. Since my null space is non-empty, and in particular my null space is -1, -1, 3, and 1, we're going to call this Z. It is going to be a solution to the homogeneous system. That tells us that I have linear combinations here, linear combinations, that are going to map my vector into the 0 vector because I solved that homogeneous system. And that tells us that if we just choose some vector x, let's just choose some vector x. I just chose 1, 2, 3, 4. Then y, this is how I'm checking. Let's see that y is equal to x plus z. Here's my x, here's my z. This is what it equals. Now, if I check this, my transformation of T on X should equal the same transformation of T onto Y. And the way that you would check it is you would put your vector X, 1, 2, 3, 4, in here and see what kicks out. It shouldn't kick out 0. And it should kick out 7, 4, and 1. Now, this is how I defined Y. I defined Y as being my X plus my Z, my kernel. And so here's my kernel. And I have 0, 1, 6, and 5. That's my Y value. That is my Y vector. And if I put these 0, 1, 6, 5 into this, not the homogeneous part, I should also get the 7, 4, and 3. So we see that this is injective. Now we have to see whether or not it is surjective. For this to be surjective, then there must not be any elements. There must not be, there should be not be an element in R3 with an empty pre-image for it to be surjective. So first we're going to compute the range of the linear transformation, find an element that may be outside this set. If we can find an element outside this set, then we know that it is not surjective. So what we're going to do is we're going to start with the spanning set of the domain. So the spanning set of the domain would be the, because we're in R4, it would be these vectors. My first vector here, which of course has 1 in the first position, my second vector, 1 in the second position, in the third position, and then in the fourth position. We know that is the spanning set for R4. It will get mapped to the first column. And so my first column is this. And the first column, when I'm talking about the first column, I'm referring back up to this matrix here, which was built, of course, by these equations, by the how that I defined my linear transformation. So that's what I'm talking about being the first column. And then, of course, to the second column, the third column, and then the fourth column. So then let's take a look at let's look at the range. So this is the range of T. That is the first, second, third, fourth column. Now we know that this is a linear dependent set. So let's go ahead and row reduce this. So go put it into matrix and row reduce it. Well, when I row reduce it, I end up with the basis. This is the basis for R3. Because this is the basis for R3, we know that T is surjective. There's nothing outside of R3. I mean, I'm getting all of R3. There's no other elements. I'm getting all of R3 from my pre-image. That means that is surjective. So it's surjective and injective. That means T must be bijective. And what that's going to mean for us in our next section, that means we can undo it. That means we can find the inverse. So we're going to do more practice of these in class, but this is just kind of giving you a taste for what injective and surjective means. We'll see you in class.